A 2014 meta-analysis in the Proceedings of the National Academy of Sciences compared 225 STEM courses. Traditional lectures hit a 33.8. A modern university instructor cannot rely strictly on their subject matter expertise. Translating a high-level understanding of quantum mechanics or macroeconomics into a digestible format requires distinct tools. It requires the discipline of knowledge engineering. To understand how to build this environment, we have to look at the physical constraints of the human brain, translate those constraints into a precise language for course design, and then align our daily classroom tactics with our long-term strategic goals. The data shows that continuing to rely solely on the traditional lecture is a failure of professional ethics. To fix the systemic issues in higher education, we have to start by understanding the biological realities of how the brain actually learns. Adult learning is a physical process. It relies on neuroplasticity, the literal structural changing of the brain as information is pulled from working memory and integrated into long-term networks, building and cementing new schemas. This physical process has strict prerequisites. The amygdala acts as a biological switch. When a student experiences high anxiety or a fear of public humiliation, the amygdala triggers a stress response that physically blocks signals from reaching the prefrontal cortex. Without a baseline of psychological safety, higher-order thinking is biologically impossible. This diagram represents cognitive load theory, established by John Sweller. It visualizes the brain's most severe bottleneck, working memory. While our long-term memory is effectively limitless, working memory can only hold between 4 and 7 units of information at any given time. Sweller identifies 3 types of cognitive load competing for this tight space. The first is intrinsic load. This is the inherent, unavoidable complexity of the material. Organic chemistry is objectively harder to process than basic addition. The second is extraneous load. This is the mental tax caused by poor instructional design. Reading text verbatim off a crowded slide, or forcing a student to flip back and forth between a graph and text, burns up working memory on useless friction. The third is germane load. This is the productive mental effort required to actually comprehend the material and build permanent schemas in long-term memory. Because working memory is so limited, novices are highly vulnerable to overload. They lack existing schemas to help them process new data. This is why beginners require highly structured, step-by-step guidance and worked examples to keep their cognitive load manageable. But as students gain expertise, their needs invert. This is the expertise reversal effect. Advanced students already have complex schemas. Forcing them to follow rigid step-by-step instructions actually generates extraneous load, interfering with existing knowledge and degrading their performance. They need autonomy and problem-solving tasks. Therefore, the primary physiological duty of an instructor is to aggressively eliminate extraneous noise. By clearing out bad design, you preserve the student's highly limited working memory, reserving it entirely for the heavy lifting of schema construction. To manage this cognitive load, educators need a way to define exactly what the brain should be doing. Broad goals like understand the topic are impossible to measure. We need a precise, standardized language for learning objectives. This illustrates the fate of the 1956 Bloom's taxonomy pyramid. In modern instructional design, the pyramid is debunked as a rigid, linear myth. The idea that students must spend years memorizing facts before they are allowed to think critically actively stifles deep learning. Benjamin Bloom never actually drew the pyramid in his original handbook. It was added by later popularizers. He considered the taxonomy a working tool for test makers. His broader legacy was heavily rooted in real-world cognitive development, heavily influencing the creation of the National Head Start program to support early childhood education. By 2001, a team led by Lauren Anderson and David Krathwell updated the taxonomy to fit modern science. They flattened the pyramid into a 2-dimensional grid. The horizontal axis tracks cognitive processes, renaming categories into active verbs: remember, understand, analyze. They also made a critical adjustment. Evaluate was moved down a step, and create was placed at the absolute peak. To create a viable new solution, you must first evaluate all existing parts and select the best ones. The vertical axis maps the knowledge dimension. The lowest tier is factual knowledge. This is the isolated vocabulary of a discipline. the chemical formulas, the dates, the specific terminology. Next is conceptual knowledge. This covers the theories, classifications, and structural relationships between the facts. It is the grammar of the discipline, allowing students to transfer their understanding from one scenario to a completely new one. Above that is procedural knowledge. This is knowing exactly how to do something, executing a specific algorithm, conducting a titration, or choosing the correct statistical test for a dataset. Finally, at the top sits metacognitive knowledge. This is the student's awareness of their own cognition. It is knowing how to act as the driver of their own brain, selecting different study strategies depending on the complexity of the task in front of them. The demand for metacognition is not a recent trend in educational psychology. The ancient imperative carved into the Temple of Apollo at Delphi, Gnothi Sauton, or Know Thyself, was the earliest requirement for this exact kind of deep cognitive awareness. Plotting precise coordinates on this matrix changes how a course operates. If a professor wants a student to analyze conceptual knowledge, they can map that exact point. It stops educators from accidentally giving a rote memorization test when they intended to assess high-level synthesis. By treating learning as the intersection of a specific action and a specific type of knowledge, universities can abandon vague syllabus descriptions. They gain the ability to write precise, executable code for human cognitive growth. However, even a perfectly written syllabus fails if it falls victim to the most common operational error in higher education: the misalignment between long-term strategy and daily tactical execution. Consider a course where the syllabus proudly states the strategic goal is the development of critical thinking, yet throughout the semester, the students are assessed entirely through multiple-choice exams that test the recall of isolated definitions. Students operate as highly rational agents managing limited resources. When forced to choose between the lofty goals written on a syllabus and the stark reality of the grading system, they will always optimize their behavior to survive the grade. This animation illustrates what researcher John Biggs called the backwash effect. It demonstrates how the tactical method of assessment dictates the student's approach to learning, sending a wave that froze backward through the course, completely washing away the original intent of the syllabus. Faced with a multiple-choice test on facts, the student abandons any attempt at critical thinking. They revert their strategy to rote memorization, cramming dates and terminology just long enough to pass the exam. The professor's grand educational strategy is thoroughly defeated, not by the students, but by the professor's own poorly designed assessment methods. It exposes a harsh reality of academic design. Students rarely learn the curriculum as it is written. They only learn the curriculum as it is assessed. John Biggs proposed a structural solution to the backwash effect called constructive alignment. This diagram shows the three elements that must be perfectly synchronized. First, the intended learning outcomes, formulated using the precise verbs of the 2D taxonomy matrix. Second, the teaching activities used in the classroom. And third, the assessment tasks used to evaluate the student. In a constructively aligned course, every node mirrors the others. If the stated goal is to analyze, the classroom activity cannot be a passive lecture, and the exam cannot ask the student to just list the facts. When these three pillars lock together, the backwash effect is neutralized. The student's path of least resistance to passing the exam becomes mathematically identical to the professor's goal of deep conceptual learning. Achieving this requires instructors to prune their delivery, removing extraneous load, to preserve space for active, aligned practice in the classroom. This shifts the role of the academic. Teaching can no longer operate as a private, intuitive art happening behind closed doors. It must function as an open, collective, and evidence-based science. By managing cognitive load, utilizing a precise taxonomy matrix, and enforcing constructive alignment, we stop arbitrarily filtering students out through bad instructional design. The modern university serves as an environment for the deliberate engineering of human minds, capable of navigating and creating the future.